Hello dear all, welcome to another session of coordination chemistry. So in today's class we'll be studying about the magnetic properties of a coordination complex explained using crystal field theory. So as we know, electrons moving in its orbital possess a magnetic moment which is equal to EH by 4mc because it acts just like a charge circulating in a circular loop. So it should definitely possess a magnetic moment mu which is equal to EH by 4 pi mc, where E is the charge of the electron, H is the Planck's constant, and M is the mass of the electron, and C is the velocity. So all these terms are a constant for a given electron, and its value is 9.274 into 10 raised to minus 21 ergs per Gauss. So this is called Bohr magneton, which is the unit of magnetic moment. Bohr magneton is the unit of magnetic moment and its value is 9.274 into 10 raised to minus 21 ergs per Gauss, which is the magnetic moment associated with an electron moving in a circular loop. So coming to coordination complexes, they can be classified into two, either diamagnetic complexes or paramagnetic complexes. That is what we learned in VBT theory as well. So what were diamagnetic substances or diamagnetic complexes and paramagnetic complexes? Diamagnetism occurs when all the electrons are paired up, so that these substances are easily repelled by a magnet, and paramagnetic substances are those substances where there is unpaired electrons and they are attracted towards a magnet. So we can use here CFT, crystal field theory, to explain these properties of a complex. So here we are given an equation mu is equal to root of n into n plus 2. This is applicable to first row transition metal ions with unpaired electrons. The number of unpaired electrons is denoted using n. That is, for any paramagnetic substance, we can calculate the magnetic moment mu using this equation for first row transition metal ions. And the equation is mu is equal to root of n into n plus 2, where n denotes the number of unpaired electrons. So that much is clear for you. Now we will see how this is calculated. Okay. So this paramagnetism can be measured by using a device called Gauss balance. It is a simple device actually. I'll show the picture. This is a Gauss balance. This is, you can see it is simply a balance, and the one side will keep the weight and the other end we are keeping a small vial where the complex is placed. The complex will be placed in this plate and the weight will be in this plate. And the complex will be suspended between a bar magnet. Here you can see the north and the south poles. So when the magnetic field is applied, it's an electromagnet, and when the magnetic field is applied, if it is a paramagnetic substance, what will happen? If this complex is a paramagnetic substance, it will be attracted towards the bar magnet, isn't it? If it is paramagnetic, it should be definitely attracted towards this magnet or towards the magnetic field. And what happens? As it is attracted downwards, we know that weight is equal to mg, mass into acceleration due to gravity. So weight, we have to put more weight here. As it is pulled downwards, we have to put more weight here. So what does that mean? In the absence of any magnetic field, if there is no magnetic field, the weight will be less, weight added will be less. But in the presence of a magnetic field, if it is a paramagnetic substance, since it is pulled down towards the magnetic field, you will have to add more weight to balance it, right? You will have to add more weight here than here when there is magnetic field. Here magnetic field is turned on, here it is not turned on. So when it is turned on, you have to add more weight in order to balance the pan. What does that mean? If it is a paramagnetic substance, the weight under the influence of the magnetic field will be more than the weight in the absence of a magnetic field. So this extra weight will give the number of unpaired electrons. So how many unpaired? It is a measure of the number of unpaired electrons in this paramagnetic complex, because n is directly proportional to mu and mu will be directly proportional to chi m, molar susceptibility, which is directly proportional to this weight. Okay. For the time being, you just know we can measure the magnetic moment of a paramagnetic substance using a Gauss balance. It is simply a balance which is used to measure the number of unpaired electrons given in a or present in a paramagnetic complex, and is directly related to the weight of the complex when it is kept in a field. This is without field and this is with field. Which field? Magnetic field. When a magnetic field is there. So I think that is clear about Gauss balance. Moving on to the next point. It is about sorry, it is how to calculate this magnetic moment mu for different number of unpaired electrons. So how we can determine this different number of unpaired electrons can be easily done by writing the outer electronic configuration of the corresponding metal ion. If it is Ti3 plus, we know scandium, titanium. Scandium D1, 3D1, 4s2, then titanium it will be 3D2, 4s2. Removing 3 electrons, since it is 3 plus, removing 3 electrons, what we will get 3D1, or it is having 1 unpaired electron. So the magnetic moment is 1 into root of 1 into 1 plus 2, which is 1.73. The theoretical values are given here. It is almost similar to the experimental values. Okay. For vanadium 3 plus, it is having 2 unpaired electrons. Just like this, you can find it out. Scandium, titanium, vanadium. Okay. So vanadium 3 plus, it is having 2 unpaired electrons, and the value for magnetic moment is 2.83. Cr3 plus, it is 3 unpaired electrons, then 3.87. Mn3 plus, it has 4 unpaired electrons, then 4.90. Fe2 plus, if it is having a 4 unpaired electrons, it is 4.90. And Fe3 plus, it is having 5 unpaired electrons, and it is giving a value of 5.9. So in similar way, we can find out the magnetic moment for any first row transition metal using this equation. Mu is equal to root of n into n plus 2, where n is the number of unpaired electrons. So let's see how crystal field theory explains the magnetic properties in detail about a complex or about a coordination complex. So here I have taken the example of CONH3 6 times 3 plus. We know that cobalt is in 3 plus oxidation state. Since cobalt 3 plus, it should be what configuration? D6 configuration. And we also know that amine NH3 is a strong field ligand, and hence the splitting will be more, or the delta value will be more. It is an octahedral complex, right? So delta O will be higher since it is a strong field ligand. Okay, this is the diagram for that. That is CONH3 6 times 3 plus. The delta or the splitting between the two sets of d orbitals will be more since NH3 is a strong field ligand. The same CO3 plus is here also. COF6 3 minus, here also the oxidation state of the cobalt is, the oxygen is small, okay. The oxidation state of this cobalt is what? 3 plus. X minus 6 is equal to minus 3. X is equal to minus 3 plus 6. So X is equal to 3 plus. They make it smaller. Cobalt, C and O. So we will get cobalt in the 3 plus oxidation state. Here also we know that it is having a D6 configuration. But we know that F minus is a weak field ligand. From the spectrochemical series, it is very much clear that F minus is a weak field ligand. So what happens? The delta O or the crystal field splitting will be less when compared to crystal field splitting in the amine complex, when the ligand is an amine. The same CO3 plus, it is the same CO3 plus here and here, but the difference is that the CO3 plus associated with NH3 will be having more delta O when compared to that of that associated with F minus, that is a weak field. So this forms a low spin complex. We always know strong field ligand, low spin complex. Weak field ligand, high spin complex. Why it is so? Because delta